Chapter 2 turns attention to finite-dimensional spaces. The central thing is that each such space can be assigned a unique integer, its dimension, which satisfies our intuitive requirements about dimensionality and becomes the principal tool for what follows. A finite-dimensional space can be characterized as one isomorphic to some coordinate space. Such an isomorphism transfers an operator there, where it acquires a matrix. So linear transformations on such spaces are mirrored completely by matrices. Back to the linear combination map of Chapter 1. The definition, a finite index set of vectors, is independent if that map is injective and is a basis for V if that map is an isomorphism. When the index set is 1 to n, it is called an ordered basis or a frame. So it is a basis exactly when every vector of V has a unique set of coefficients. The coefficients exist because the vectors span V, and they are unique because the vectors are independent. The book gives an example: two concrete vectors in the plane. Checking that they form a basis is checking that the vector equation has a unique solution for every target, which splits into two scalar equations and yields to secondary school elimination. The more usual definition of independence is here a corollary. The vectors are independent exactly when coefficients times vectors summing to 0 forces every coefficient to be 0. That says precisely that the null space contains only 0. An ordered basis gives each vector a unique set of coefficients, called its coordinate tuple. The combination map is called the basis isomorphism, and its inverse the coordinate isomorphism. Taking the jth coordinate is a linear functional, the jth coordinate functional. Now to show every finite-dimensional space has a basis. Two small remarks first. An index set can be independent only if the indexing is injective, and any subset of an independent set is independent. The lemma: if a set is independent and some vector is not in its span, adjoining that vector leaves it independent. For if a non-trivial combination vanished, the new vector's coefficient could not be 0, and then it could be solved for, putting it in the span. With that lemma, one can pick a basis out of a finite spanning set by running through it and keeping the members that actually enlarge the linear span. That is intuitive but messy to set up rigorously, so the book proceeds differently. The theorem: any minimal finite spanning set is a basis, so any finite dimensional space has one, and any finite independent subset can be extended to a basis. Coordinate space has one special basis, the Kronecker delta functions, whose basis isomorphism is the identity.